can hope that's all it is. Good morning, everyone. So today we're going to do some algorithms, back to algorithms. And we're going to use a lot of the, well, some of the simpler mathematics that we developed last class, like the master theorem for solving recurrences. We're going to use this a lot because we're going to talk about recursive algorithms today. And so we'll find their running time using the master theorem. This is just the same as it was last time, I hope, unless I made a mistake. Yeah, a couple of reminders. You should all go to recitation on Friday. That's required. If you want to, you can go to homework lab on Sunday. That may be a good excuse for you to actually work on your problem set a few hours early. Actually, it's due on Wednesday, so you've got lots of time. And there's no class on Monday. It is the holiday known as student holiday, so don't come. Today, we're going to cover something called divide and conquer. Also known as divide and rule, or divide et imperia, for those of you who know Latin, which is a tried and tested way of conquering a land by dividing it into sections of some kind, could be different political factions, different whatever, and then somehow making them no longer like each other, like starting a family feud is always a good method. So you should remember this on your quiz. I'm kidding. And if you can separate this big power structure into little power structures so that you dominate each little power structure, then you can conquer all of them individually, as long as you make sure they don't get back together. So that's divide and conquer, as practiced, say, by the British. But today we're going to do divide and conquer as practiced in Corman, Lancerson, Rivest-Stein, or every other algorithms textbook. This is a very basic and very powerful algorithm design technique. So this is our first real algorithm design experience. We're still sort of mostly in the analysis mode, but we're going to do some actual design. We're going to cover maybe only 3 or 4 major design techniques. This is one of them, so it's really important. And it will lead to all sorts of recurrences, so we'll get to use everything from last class, see why it's useful. So as you might expect, the first step in divide and conquer is divide, and the second step is conquer. But you may not have guessed that there are 3 steps, and I'm leaving some blank space here, so you should too. So divide and conquer is an algorithmic technique. You're given some big problem you want to solve. You don't really know how to solve it in an efficient way, so you're going to split it up into subproblems. That's the divide. You're going to divide that problem, or more precisely, the instance of that problem, the particular instance of that problem you have, into subproblems. And those subproblems should be smaller in some sense. And smaller means normally that the value of n is smaller than it was in your original problem. So you sort of made some progress. Now you have one or more likely you have several subproblems you need to solve. Each of them is smaller, so you recursively solve each subproblem. That's the conquer step. So you conquer each subproblem recursively, and then somehow you combine those solutions into a solution for the whole problem. So this is the general divide and conquer paradigm, and lots of algorithms fit it. You've already seen one algorithm that fits this paradigm, if you can remember. Merge sort, good. Wow, you're all awake. I'm impressed. So we saw merge sort, and if I'm clever, I could fit it in this space. Sure, let's be clever. So quick review on merge sort, phrased in this 1, 2, 3 kind of method. The first step was to divide your array into 2 halves. This really doesn't mean anything because you just sort of think, oh, I'll pretend my array is divided into 2 halves. You don't have to, there's no work here. This is 0 time. You just look at your array. Here's your array. I guess maybe you compute n over 2 and take the floor. Okay, that takes constant time. And you say, okay, I'm pretending my array is now divided into the left part and the right part. And then the interesting part is that you recursively solve each one. That's the conquer. So we recursively sort each subarray. And then the third step is to combine those solutions. And so here we really see what this means. We now have a sorted version of this array by induction. We have a sorted version of this array by induction. We now want a sorted version of the whole array. We saw that was the merge problem, merging 2 sorted arrays. And that we saw how to do in linear time, order n time. So I'm not going to repeat that, but the point is it falls into that framework. I want to write the running time of merge sort as a recurrence. I mean, you've already seen the recurrence. You've already been told the solution, but now we actually know how to solve it. And furthermore, every algorithm that follows the divide and conquer paradigm will have a recurrence of pretty much the same form, very much like our good friend the master method. So let's do it for merge sort where we sort of already know the answer, get a bit of practice. So this is the merge sort recurrence. You should know and love this recurrence because it comes up all over the place. It comes from this general approach by just seeing what are the sizes of the subproblems you're solving and how many there are and how much extra work you're doing. So you have here the size of the subproblems. It happens here that both subproblems have the same size, roughly. There's this sloppiness that we have, which really should be t of floor of n over 2 plus t of ceiling of n over 2. And when you go to recitation on Friday, you'll see why that's OK. The floors and ceilings don't matter. There's a theorem you can prove that that's happy. You can assume that n is a power of 2. OK? But we're just going to assume that for now. So we just have 2 problems of size n over 2. This 2 is the number of subproblems. And this order n is all the extra work we're doing. Now, what's the extra work? Potentially, well, the conquering is always just recursion. So there's sort of no work there except this lead part. The dividing, in this case, is trivial, but in general, it might involve some work. And the combining here involves linear work. So this is the divide and conquer running times. So this is the non-recursive work, right? And that's generally how you convert a divide and conquer algorithm into a recurrence. It's really easy, and you usually get to apply the master method. Here, we are in case 2. Very good. This is case 2. And k is 0 here. And so in the recursion tree, all of the costs are roughly the same. They're all n to the log base b of a. Here, n to the log base 2 of 2 is just n. So these are equal. So we get an extra log factor because of the number of levels in the recursion tree. Remember the intuition behind the master method. So this is n log n, and that's good. Merge sort is a fast sorting algorithm, n log n. Insertion sort was n squared. In some sense, n log n is the best you can do. We'll cover that in 2 lectures from now, but just foreshadowing. Okay, today we're going to do different divide and conquer algorithms. So sorting is one problem. There's all sorts of problems we might want to solve. So it turns out a lot of them you can apply divide and conquer to. Not every problem. Like how to wake up in the morning, it's not so easy to solve a divide and conquer, although maybe you could. Maybe that's a good problem set problem. Okay. The next divide and conquer algorithm we're going to look at is even simpler than sorting, even simpler than merge sort, but it drives home the point of when you have only one subproblem. How many people have seen binary search before? Anyone hasn't? One. Okay. I will go very quickly then. So you have some element x. You want to find x in a sorted array. How many people had not seen it before they saw it in recitation? No one. Okay, good. You just see it in another class. Probably 6001 or something. Very good. You took the prerequisites. Okay. So I just want to phrase it as a divide and conquer because you don't normally see it that way. So you compare, the divide step is you compare x with the middle element in your array. Then the conquer step, so here's your array. Here's the middle element. You compare x with this thing. If, let's say, x is smaller than the middle element in your array, you know that x is in the left half because it's sorted. Nice loop invariant there, whatever. But we're just going to think of that as recursively. I'm going to solve the problem of finding x in this subarray. So we recurse in one subarray. Unlike merge sort where we had two recursions. And then the combined step, we don't do anything. I mean, if you find x in here, then you found x in the whole array. There's nothing to bring it back up, really. So this is just phrasing binary search as in the divide and conquer paradigm. It's kind of a trivial example, but there are lots of circumstances where you only need to recurse in one side. And it's important to see how much of a difference making one recursion versus making two recursions can be. So here we have, this is the recurrence for binary search. We start with a problem of size n. We reduce it to 1. There's an implicit 1 factor here. One problem, subproblem of size n over 2, roughly. Again, floors and ceilings don't matter. Plus a constant, which is to compare x with the middle element. So it's actually like one comparison. This has solution log n. And you all know the running time of binary search. But here it is at solving the recurrence. And I mean, there are a couple differences here. We don't have the additive order n term. If we did, it would be linear, the running time. Still better than n log n. So we're getting rid of the 2, bringing it down to a 1, taking the n, bringing it down to a 1. That's making the running time a lot faster, a whole factor of n faster. Okay, no big surprise there. Let's do some more interesting algorithms. So the powering a number problem is I give you a number x. Think of that as like a real number or floating point number, whatever. And I give you an integer n, at least 0. I want to compute x to the power n. Okay, so it's a very simple problem. It's in some sense even easier than all of these. But here it is, and divide and conquer is sort of the right thing to do. So the naive algorithm is very simple. How do you compute x to the power n? Well, the definition of x to the power n is I take x and I multiply by x n times. So I take x times x times x times x, where there are n copies of x total. And that's x to the n. No big surprise. That's n multiplications, or n minus 1 multiplications, theta n time. Okay, but that's not the best you can do for this problem. Any suggestions on what we might do using divide and conquer? For someone, has anyone seen this algorithm before? Few. Okay, so for the rest. Testing on-the-spot creativity, which is very difficult, but I always like a challenge. So random ideas. What could we possibly do to make this problem, solve this problem in less than linear time? How is this sort of a divide and conquer problem? We have two inputs, x and n. Yeah. So we could try to divide on x. Seems a bit hard, it's just some number. Or we could try to divide on n. Any guesses? Look at x to the n over 2. Very good. That's exactly the idea of the divide and conquer algorithm. So we'd like to look at x to the n over 2. This is going to be a little bit tricky. Now we are going to have to pay attention to floors and ceilings. What I would like to say is, well, x to the n is x to the n over 2 times x to the n over 2. And this is true if n is even. If it's odd, then I need to be a little bit more careful. But let's just think about the intuition why this is a good divide and conquer algorithm. We have a problem of size n, let's say. We convert it into, it looks like two subproblems of size n over 2. But in fact, they are the same subproblem. So I only have to solve one of them. If I compute x to the n over 2, hey, I know x to the n over 2. So there's one recursive call to a problem of size n over 2. Then I square that number, and that's one computation. So exactly the same recurrence as binary search, log n time, much better than n. Cool. Okay, I also have to solve the odd case. So n is odd. I'll look at n minus 1 over 2. That's n minus 1 better be even. And then I'm missing another factor of x. So if n is odd, I'm going to have to do one recursive call and two multiplications, same recurrence. One recursive problem of size n over 2 plus constant time to do the dividing work here is dividing by 2. And the combination work is doing one or possibly two multiplications. And this is log n. Okay, and if all you're allowed to do is multiply numbers, log n is the best you can do. Good. So simple but powerful. Hey. Whenever you want to compute a power of a number, now you know what to do. Does anyone not know the definition of Fibonacci numbers and is willing to admit it? Okay, yeah, so this is a good old friend. I'll write down the definition, just reminder, in particular, the base cases. So Fibonacci numbers, I will claim, are very important because it appears throughout nature. You look at certain fruits, you see the Fibonacci sequence if you count the number of little bumps around each ring. If you look at the sand in the beach and how the waves hit it, it's a Fibonacci sequence, I'm told. You look all over the place, Fibonacci sequence is there. So how does nature compute the Fibonacci sequence? Well, that's a different class, but how are we going to compute the Fibonacci sequence as fast as possible? You've probably seen two algorithms. I'll call them, so the most naive algorithm is a recursive algorithm, where you say, okay, f of n, I say, well, if n is 0, return 0. If n is 1, return 1. Otherwise, recursively compute f of n minus 1 and f of n minus 2, add them together. How much time does this algorithm take? For those who have seen it before. It's not obvious to guess. It doesn't have to be exact, but okay, how many people have seen this algorithm before and analyzed it? Yep. Half. Okay, so what's the running time? Really, really long. Very good. Any more precise answers? Just one. What's that? Exponential, yes. That's also correct and more precise. I'll be even more precise. Maybe you haven't seen this analysis before. It's phi to the n where phi is the golden ratio. Again, golden ratio appears throughout the world in mathematics, but this is probably the only time in this class, I'm afraid. But there we go. It made its cameo, so we're happy. Okay, this is called exponential time. I mean, this is bigger than 1. That's all you need to know. This is exponential time. Meaning, exponential time means basically some constant to the power n. Exponential time is a very long time. It's bad. Okay? Polynomial time is good. So, this is what we want are polynomial time algorithms. This class is basically entirely about polynomial time algorithms. Question? Say what the algorithm does again. So it just f of n, so define function Fibonacci of n. I check for the base cases, and otherwise I recursively call Fibonacci of n minus 1. I recursively call Fibonacci of n minus 2, add those two numbers together. So you get this branching tree. You're solving two subproblems of almost the same size, just additively smaller by 1 or 2. So you have, I mean, you're almost not reducing the problem size at all. So that's intuitively why it's exponential. You can draw out a recursion tree, and you'll see how big it gets, how quickly. I mean, by n over 2 levels, you've only reduced on one branch the problem from n to n over 2. The other one, maybe you've gotten from n down to 1, but none of the branches have stopped after n over 2 levels. So you have at least 2 to the power n over 2, which is like square root of 2 to the power n, which is getting close to phi to the n. Okay, so it's definitely exponential. And exponential is bad. We want polynomial. Okay, n squared, n cubed, log n would be nice. Anything that's bounded above by a polynomial is good. This is an old idea. It goes back to one of the main people who said polynomial is good is Jack Edmonds, who's famous in the combinatorial optimization world. He's my academic grandfather on one side. And right. He's a very interesting guy. Okay, so that's a really bad algorithm. You've probably seen a somewhat better algorithm, which you might think of as the bottom-up implementation of that recursive algorithm. Or another way to think of it is if you build out the recursion tree for Fibonacci of n, you see that there's lots of common subtrees that you're just wasting time on. You know, when you solve Fibonacci of n minus 1, it again solves Fibonacci of n minus 2. Why solve it twice? You only need to solve it once. So it's really easy to do that if you do it bottom up, but you could also do it recursively with some cache of things you've already computed. So no big surprise. You compute the Fibonacci numbers in order. And at each time when you compute Fibonacci of n, let's say, you have already computed the previous two. You add them together, it takes constant time. So the running time here is linear. Linear in n. N is our input. Great. Is that the best we can do? No. So any ideas on how we could compute Fibonacci of n faster than linear time? So now we should diverge from what you've already seen, for most of you. Any ideas using techniques you've already seen? Yes?
Well, maybe it's cheating then, but there's the neat mathematical trick with phi and psi to the nth powers.
Yes, we can use the mathematical trick of phi and psi to the nth powers. In fact, you can just use phi, phi, pho, fum, whatever you want to call this letter. Greek letter. Good. So here's the mathematical trick. And indeed, this is cheating, as you said. This is no good, but so it is. We'll call it naive recursive squaring. I'm going to say, well, we know recursive squaring. Recursive squaring takes log n time. Let's use recursive squaring. And if you happen to know lots of properties of the Fibonacci numbers, you don't have to, but here's one of them. If you take phi to the n divided by root 5, and you round it to the nearest integer, that is the nth Fibonacci number. Okay, this is pretty cool. Fibonacci of n is basically phi to the n. So we could apply recursive squaring to compute phi to the n in log n time, divide by root 5, assume that our computer has an operation that rounds a number to its nearest integer, and poof, we're done. That doesn't work for many different reasons. Depending on a real machine, probably you'd represent phi and root 5 as floating point numbers, which have some fixed amount of precise bits. And you do this computation, you'll lose some of the important bits, and when you round to the nearest integer, you won't get the right answer. So floating point roundoff will kill you on a floating point machine. On a theoretical machine, where we magically have numbers that can do crazy things like this, usually, it really takes more than constant time per multiplication. So we're sort of in a different model. You can't multiply phi times phi in constant time. That's sort of outside the boundaries of this course, but that's the way it is. Yeah. In fact, in a normal machine, some problems you can only solve in exponential time. In a machine where you can multiply real numbers and round them to the nearest integers, you can solve them in polynomial time. So it really breaks the model. You can do crazy things if you were allowed to do this. This is not allowed. And I'm foreshadowing like 3 classes ahead, or 3 courses ahead, so I shouldn't talk more about it. But it turns out we can use recursive squaring in a different way if we use a different property of Fibonacci numbers. And then we'll stick with integers and everything will be happy. Don't forget to go to recitation. If you want to homework lab, don't come here on Monday. That's required. Okay. So this is sort of the right recursive squaring algorithm. And this is a bit hard to guess if you haven't already seen it. So I will just give it to you. Turns out, I'll call this a theorem. First time I get to use the word theorem in this class. Turns out the nth Fibonacci number is the nth power of this matrix. Cool. If you look at it a little bit, you say, oh yeah, of course. We'll prove this theorem in a second. But once we have this theorem, we can compute f of n by computing the nth power of this matrix. It's a 2 by 2 matrix. You multiply 2 by 2 matrices together, you get a 2 by 2 matrix. So that's constant size, 4 numbers. I can handle 4 numbers. Okay, we don't have crazy precision problems on the floating point side. It's only 4 numbers to deal with. Matrices aren't getting bigger. So the running time of this divide and conquer algorithm will still be log n, because it takes constant time per 2 by 2 matrix multiplication. Yes, Martin?
The right upper corner for the left upper corner.
Oh, yes. Thank you. I have a type error. Sorry about that. F of n is indeed the upper left corner, I hope. Better check I don't have an off by 1. I do. It's Fn upper right corner. Indeed, that's what you said. F of n. Need more space, sorry. I really ought to have a 2 by 2 matrix on the left-hand side there. Thank you. So I compute this nth power of a matrix in log n time. I take the upper right corner or the lower left corner, your choice. That's the nth Fibonacci number. So this implies an order log n time algorithm with the same recurrence as the last 2, binary search and really the recursive squaring algorithm. Log n plus a constant, so log n. So let's prove that theorem. Any suggestions on what techniques we might use for proving this theorem? Or what technique, singular? Induction, very good. I think any time I ask that question, the answer is induction. So hint for the future. In this class. friend of mine, when he took an analysis class, whenever the professor asked, and what's the answer to this question? The answer was always 0. If you've taken an analysis class, that's funny. But okay. Maybe I'll try to ask some questions that are, whose answers are 0, just for our own amusement. So we're going to induct on n. It's pretty much the obvious thing to do. But we have to check some cases. So the base case is we have this to the first power, and that is itself, 1, 1, 1, 0. And I should have said n is at least 1. And you can check that this is supposed to be f2, f1, f1, f0. And you can check it is. f0 is 0, f1 is 1, and f2 is 1. Good. Base case is correct. Step case is about as exciting, but heck, you've got to prove that your algorithm works. So suppose we have, this is what we want to compute. And I'm just going to sort of, there's many ways I could do this. I'll just do it the fast way because it's really not that exciting. Which direction? Let's do this direction. Okay, I want to use induction on n. So if I want to use induction on n, presumably I should use what I already know is true. If I decrease n by 1, I have this property that this thing is going to be 1, 1, 1, 0 to the power n minus 1. So this I already know is, by the induction hypothesis, 1, 1, 1, 0 to the n minus 1. So presumably I should use it in some way. This equality is not yet true, you may have noticed. Okay, so I need to add something on. What could I possibly add on to be correct? Well, another factor of 1, 1, 1, 0. So this is proof by, I mean, the way I'm developing this proof is the only way it could possibly be. In some sense. If you know it's induction, this is all you could do. And then you check, indeed, this equality holds conveniently. So, for example, fn plus 1 is the product of these two things. So it's this row times this column. So it's fn times 1 plus fn minus 1 times 1, which is indeed the definition of fn plus 1. And you could check all 4 of the entries. This is true. Great. So if that's true, then I just put these together. That's 1, 1, 1, 0 to the n minus 1 times 1, 1, 1, 0, which is 1, 1, 1, 0 to the n. End of proof. So very simple proof, but you have to do that in order to know this algorithm really works. Good. Question?
Yeah, you took on the left, but another fn minus 1 in the lower right.
Oh yes, thank you. This, in the lower right, we should have fn minus 1. Yeah, this is why you should really check your proofs. We would have discovered that when I checked that this was that row times that column. But that's why you're here, to fix my bugs. It's the great thing about being up here instead of in a quiz. Okay, but that's a minor mistake. You wouldn't lose much for that. Right, so more divide and conquer algorithms. Still, we've done relatively simple ones so far. In fact, the fanciest has been merge sort, which we already saw, so that's not too exciting. The rest have all been log n times. So let's break out of the log n world. Whoops. Well, you all have the master method memorized, right? So I can erase that. Good. This would be a good test. Next problem is matrix multiplication. Following right up on this 2 by 2 matrix multiplication, let's see how we can compute n by n matrix multiplications. So, just for a recap, you should know how to multiply matrices, but here's the definition so we can turn it into an algorithm. You have two matrices A and B, which are capital letters. The ijth entry, ith row, jth column is called little aij or little bij. And your goal is to compute the product of those matrices. I should probably say that I and j range from 1 to n. So they're square matrices. The output is to compute C, which has entry Cij, which is the product of A and B. And for a recap, the ijth entry of the product is the sum, well, it's the inner product of the ith row of A with the jth column of B. But you can write that out as a sum, like so. So we want to compute this thing for every I and j. So what's the obvious algorithm for doing this? Well, for every I and j, you compute this sum. You compute all the products, you compute the sum. So it's like n operations here, roughly. I mean, like 2n minus 1, whatever. It's order n operations. There's n squared entries of C that I need to compute, so that's n cubed time. We'll write this out just for the programmers at heart. Here's the pseudocode. It's rare that I'll write pseudocode, and this is a simple enough algorithm that I can write it in gory detail. But it gives you some basis for this analysis if you'd like to program. So it's a triply nested for loop. And I made a coding error. So in here, hopefully you haven't written that far yet. I need Cij to be initialized to 0, and then I add to Cij the appropriate product, A, I, K, B, K, J. So that's the algorithm. And the point is you have a nesting of n for loops from 1 to n. That takes n cubed time, because this is constant, and that's constant. So very simple, n cubed. Let's do better. And of course, we're going to use divide and conquer. Now, how are we going to divide a matrix? There's a lot of numbers in a matrix, n squared of them in each one. There's all sorts of ways you could divide. So far, all of the divide and conquers we've done have been a problem of size n into some number of problems of size n over 2. So I'm going to say I start with some matrices of size n by n. I want to convert it down to something like n over 2 by n over 2. Any suggestions how I might do that? Yeah? Block form of the matrix, indeed. That's the right answer. So this is the first divide and conquer algorithm. This will not work, but it has the first idea that we need. So we have an n by n matrix. We can view it, this equality is more of a, you can think of it as really the same thing, a 2 by 2 block matrix where each entry in this 2 by 2 block matrix is a block of n over 2 by n over 2 submatrices. So I'll think of C as being divided into 3 parts, R, S, T, and U. Even though I write them as lowercase letters, they're really matrices. Each is n over 2 by n over 2. And A, I'll split into A, B, C, D times. B, I'll split into E, F, G, H. Okay, why not? This is certainly true, and if you've seen some linear algebra, this is basically you can do with matrices. So now I can look at R. I can pretend these are 2 by 2 and sort of forget the fact that these little letters are matrices. Just say, well, R is the product, the inner product of this row with this column. So it's AE times F times BG. Okay, let me not cheat. This would be too easy. R is AE plus BG. S is AF plus BH. T is CE plus DF. And U is DG. Thank you. Is CF plus DH. It's nothing like making it too hard on yourself. Okay, got them right? Good. So, I mean, this is just a fact about how you would expand out this product. And so now we have a recursive algorithm. In fact, we have a divide and conquer algorithm. We start with our n by n matrix. We divide it into, well, we have two of them actually. We divide it into 8 little pieces, A, B, C, D, E, F, G, H. Then we compute these things, and that gives us C just by sticking them together. Now, how do we compute these things? Well, these innocent-looking little products between these two little numbers are actually recursive matrix multiplications, because each of these little letters is an n over 2 by n over 2 matrix, so I have to recursively compute the product. So there's like 8 recursive multiplications of n over 2 by n over 2 matrices. That's what bites us. And then there's like 4 additions, plus minor work of gluing things together. Okay, how long does it take to add 2 matrices together? N squared. So this is cheap. This takes n squared. Remember, we're trying to beat n cubed for our matrix multiplication. Addition is a really easy problem. You just have to add every number. There's no way you can do better than n squared. So that's not recursive. That's the nice thing. But the bad thing is we have 8 of these recursions. So we have t of n is 8 times t of n over 2 plus theta n squared. And I've erased the master method, but you should all have it memorized. So what's the solution to this recurrence? Theta of n cubed. That's annoying. Right? So a is 8, b is 2, log base 2 of 8 is 3. Every computer scientist should know that. So log base n to the log base b of a is n cubed. That's polynomially larger than n squared. So we're in case 1. Good, thank you. Let's get them upside down. So this is n cubed, no better than our previous algorithm. Kind of sucks. And now comes the divine inspiration. Let's go over here. You know, there are some algorithms like this Fibonacci algorithm where if you sat down for a little while, it's no big deal, you'd figure it out. I mean, it's kind of clever to look at that matrix and then everything works happy. It's not obvious, but not that amazingly clever. This is an algorithm that is amazingly clever. You may have seen it before, which steals the thunder a little bit. But it's still really, really cool. So you should be happy to see it again. And how Strassen came up with this algorithm, he must have been very clever. So the claim, the idea, we've got to get rid of these multiplications. I don't really care how many. I could do 100 additions. That only costs theta n squared. I have to reduce this 8 to something smaller. Turns out if you try to split the matrices into 3 by 3 or something, that doesn't help you. You get the same problem. Because we're using fundamentally the same algorithm, just in a different order. We've got to somehow reduce the number of multiplications. We're going to reduce it to 7. The claim is that if we have 2 2-by-2 matrices, we can take their product using 7 multiplications. If that were true, we'd reduce the 8 to a 7 and presumably make things run faster. Okay, we'll see how fast in a moment. You can compute it in your head if you are bored and like computing logs, the non-integral logs. And go ahead. All right, so here we are, P1. So this algorithm is unfortunately rather long. But it's only 7 multiplications. So each of these P's is a product of 2 things, which only involves addition or subtraction. Same thing. And running out of space. It's the seventh one, actually. So those are 7 multiplications, and I can compute those in 7 times t of n over 2. Oh. Indeed it is. So 6 was wrong. 6 and 7 are the same. Very good. You know, you'd think that copying something would not be such a challenging task. But when you become an absent-minded professor like me, then you'll know how easy it is. Okay, we have them all correct, hopefully. Okay, we continue. That wasn't enough. Of course, we have 7 things. Clearly, we have to reduce this down to 4 things, the elements of C. So here they are. The elements of C, R is TU. Turns out R is P5 plus P4 minus P2 plus P6. Of course, didn't you all see that? S is, this one's really easy, P1 plus P2. T is P3 plus P4. That's clearly how they were chosen. And then U is another tricky one. Okay, now, which one of these would you like me to check? Don't be so nice. How about S? I could show you S is right. Any preferences? Oh, U. Oh no, sign errors. Okay, here we go. So the claim is this really works. You have to check all 4 of them. And I did in my notes. But U is P5. P5 is A times E plus A times H plus D times E plus D times H. That's P5. Check me. If I screw up, I'm really hosed. So AF minus AH is P1. P3 has a minus sign in front. So that's C times E plus D times E. And then we have minus P7, which is a big one. A times E plus A times F minus C times E minus C times F. Okay, and now I need like the assistant that crosses off things in parallel like the movie, right? A times H. D times E. A times F. C times E. Double sign. C. A-E, thank you. And well, hopefully these survive. D times H minus minus C times F. And if we're lucky, that's exactly what's written here, except in the opposite order. Now, magic, right? Where the hell did Strassen get this? You have to be careful. It's okay that the plus is in the wrong order, because plus is commutative. But the multiplications better not be in the wrong order, because multiplication over matrices is not commutative. So check C times F, okay, D times H. They're in the right order. Whew. I won't check the other 3. That's matrix multiplication. In hopefully subcubic time, let's write down the recurrence. T of n is now 7. Maybe I should write down the algorithm for kicks. Why not? Assuming I have time. Lots of time. So last lecture I was 10 minutes early. I ended 10 minutes early. I apologize for that. I know it really upsets you. And I didn't realize exactly when the class was supposed to end. So today I get to go 10 minutes late, right? Okay, good. I'm glad you all agree. I'm kidding. Okay, algorithm. So this is Strassen. So first we divide, then we conquer, then we combine, as usual. Don't have it written anywhere here. Fine. Divide A and B. Okay, this is sort of trivial. Then we compute the terms. For the products. So this means we get ready to compute all the p's. We compute a plus b, c plus d, g minus e, a plus d, e plus h, and so on. All of the terms that appear in here, we compute those. That takes n squared time because it's just a bunch of additions and subtractions. No big deal. Constant number of them. Then we conquer by recursively computing all the PIs. So that's each a product. There's 7 of them. So we have P1, P2, up to P7. Yeah. And finally, we combine, which is to compute RS, T, and U. And those are just additions and subtractions again, so they take n squared time. So here we finally get an algorithm that is non-trivial both in dividing and in combining. Recursion is always recursion, but now we have interesting steps 1 and 3. So the recurrence is T of n is 7 recursive subproblems, each of size n over 2, plus order n squared to do all this addition work. So now we need to solve this recurrence. We compute n to the log base b of a, which here is n to the log base 2 of 7. And log base 2 of, well, we know log base 2 of 8 is 3. Log base 2 of 7 is going to be a little bit less than 3, but still bigger than 2, because log base 2 of 4 is 2. So it's going to be polynomially larger than n squared, but it's polynomially smaller than n cubed. So we're again in case 1. And this is the cheating way to write log base 2 of 7. Is log base, LG means log base 2. You should know that. It's all over the textbook and in our problem sets and whatnot. And to the log base 2 of 7. And in particular, so if I have my calculator, here's my calculator. Nope. Here. Yes. It's a good old-fashioned calculator. Okay, it is, no, that's wrong. Sorry. It's strictly less than 2.81. So that's cool. I mean, it's polynomially better than n cubed. Still not as good as addition, which is n squared. It's generally believed, although we don't know whether you can multiply as fast as you can divide for matrices. We think you can't get n squared, but who knows? Could still happen. There's no lower bounds. This is not the best algorithm for matrix multiplication. It's sort of the simplest that beats n cubed. The best so far is like n to the 2.376. Getting closer to 2. Okay, you might think these algorithms are a bit, these numbers are a bit weird. Maybe the constants out here dominate the improvement you're getting in the exponent. Turns out improving the exponent is a big deal. I mean, as n gets larger, exponents really come out to bite you. So n cubed is pretty impractical for any very large values of n. Strassen definitely beats, and we know that Strassen will beat normal matrix multiplication if n is sufficiently large. The claim is roughly n about 32 or so, already you get an improvement. For other reasons, not just because the exponent gets better, but there you go. So this is pretty good. This is completely impractical, so don't use whatever this algorithm is. I don't have the reference handy, but it is just trying to get a theoretical improvement. There may be others that are in between and more reasonable, but that is not it. Wow. Lots of time. Any questions? We're not done yet, but any questions before we move on? from matrix multiplication. Okay, I have one more problem. Divide and conquer is a pretty general idea. I mean, you can use it to dominate countries. You can use it to compute, multiply matrices. I mean, who would have thought? Here's a very different kind of problem you can solve with divide and conquer. It's not exactly an algorithmic problem, although, I mean, in some sense, it's computer science. This is very large-scale integration. Okay, the chips, you know, they're very large-scale integrated. Probably even more these days, but that's the catchphrase. So here's a problem, and it arises in VLSI layout. I won't get into too many details why, but you have some circuit, and here I'm going to assume that the circuit is a binary tree. Okay, this is just part of a circuit. Assume for now, I mean here, there's just a complete binary tree. Okay, complete binary tree looks like this. You know, in all of my teachings, I have drawn this figure for sure the most. It's my favorite figure, the height for a complete binary tree. Okay, there it is. I have some tree like that as some height. I want to embed it into some chip layout on a grid. Okay, that's the, let's say it has n leaves. I want to embed it into a grid with minimum area. There's a very cute problem, and it really shows you another way in which divide and conquer is useful. A powerful tool. So I have this tree. I like to draw it in this way. I want to somehow draw it on the grid. So what that means is the vertices have to be embedded onto dots in the grid. I'm talking about the square grid. So it has to go to vertices of the grid. And these edges have to be routed as sort of orthogonal paths between one dot and another. So that should be an edge, and they shouldn't cross and all these good things. So wires don't like to cross. Okay, so there's the obvious way to solve this problem, and there's the right way. And let's talk about both of them. Neither of them is particularly obvious, but divide and conquer sort of gives you a hint in the right direction. So the naive embedding, I seem to like the word naive here. Okay, I'm going to draw this bottom up because it's easier. So leave 3 grid lines and then start drawing. We have, I don't know how big that's going to be. So here's the bottom of our tree. This is like a little 3 nodes there. And then I leave a blank column. And then a blank column. I don't actually need to leave those blank columns, but it makes a prettier drawing. Okay, and then we work our way up. Okay, there's the tree, which should be aligned. On a grid, no crossings, everything's happy. How much area does it take? Well, area is, and by area I mean sort of the area of the bounding box. So I count this blank space even though I'm not using it. Count all of this blank space even though I'm not using it. So I want to look at the height. Let's call this h of n. And to look at the width, which I'll call w of n. Now it's probably pretty obvious that h of n is like log n, w of n is like n, 2n, whatever. But I want to write it as a recurrence because that will inspire us to do the right thing. So h of n, well, if you think of this as a recursion tree in some sense, we start with the big tree, we split it into 2 halves, 2 subtrees of size n over 2 indeed, because we're counting leaves. So it's exactly n over 2 on each side. Then for height, they are in parallel, so it's no big deal. The height is just the height of this thing, one of these subproblems, plus 1. The width, you have to add together the two widths and also add on 1. You don't have to add on 1 here, but it doesn't matter. Certainly at most 1. So h of n is just one subproblem of size n over 2 plus theta 1. There you do have to add 1. And w of n, let me go down here, leave a space so we can solve that. W of n is 2 times w of n over 2 plus order 1. Okay, and the usual base cases. I mean, these are recurrences we should know and love. This is log n. I've sort of already given away the answers. And this better be linear. This is, again, case 1. N to the log base 2 of 2 is n, which is the answer, much bigger than 1. And here, n to the log base 2 of 1 is n to the 0, which is 1, which is the same, so we get log n. Okay. So the area is n log n. But if you're making chips, you want the area as small as possible so you can fit more good stuff in there. So we would like to aim for, well, we certainly can't do better area than n. Got to put those leaves down somewhere. Well, it's already pretty good. It's only a log factor off, but we want to aim for n. Now, how could we get n? Any guesses on what needs to change in this layout? Not how to do it, because that's not obvious. But in terms of in terms of height and width, what should we do? Okay, it's pretty hard to get the height smaller than log n, I'll tell you. Because this is a tree, can't really get its width down less than log n. So what could we do to make the product linear? Just random ideas. What are two functions whose product is n? Square root of n and square root of n. That's a good choice. Were there other suggestions? N times constant. Yeah, n times constant would be nice, but I claim you can't get either of these down to less than the constant. You could aim for n over log n by log n. That's more likely, but I think that's also impossible. Okay, but root n by root n is the right answer, so let's go with that. So root n by root n. We haven't seen any recurrences whose solution is root n, but surely they are out there. So let's say goal is to get w of n equals to theta root n, and to get h of n equals to theta root n. If we could do that, we'd be happy, because then the area, the product, is linear. So how? What's a recurrence that is in the usual master method form whose solution is root n? I mean, you could think of it that way. Recurrence is a bit tricky. Let's just think of n to the log base b of a. When is n to the log base b of, when is log base b of a half? Because then n to the log base b of a is root n, and there's some hope that I could get a root n solution to recurrence. This is designed by knowing that it's divide and conquer, and therefore it must be something like this. So it's easy once you know the approach you're supposed to take, and you could try this approach. So when is log base b of a half? Lots of solutions. Shout them out. 4 and 2. That's a good one. Turns out log, better get this right, log base 4 of 2 is a half. Right? Because square root of 4 is 2. So let's aim for this. Why not? So when would we get log base 4 of 2? Well, t of n would be, now get this right, this is b, this is a. So it should be 2 times t of n over 4 plus something. And if I want the n to the log base b of a to dominate, it's got to be polynomially smaller than root n. So this should be n to the 1/2 minus epsilon for some epsilon, but could be smaller. Could be 1. Could be 0 would be nice, but that's probably too much to hope for. So something smaller, strictly polynomially smaller than root n. Okay, that's our goal. And now comes the magic. If you played with this a while, you would find it, I think, at this point. When you know you're supposed to somehow solve this problem of size n with 2 subproblems of size n over 4, what could you do? Well, if you start thinking of things as squares, this is the natural thing that happens. This is called the H layout. You can imagine why. It'd be much easier to draw if I had grid board, graph board, whatever, if that exists. Okay, this is a recursive layout. I'm only going to draw it a couple iterations, but hopefully you can imagine the generalization. Okay, so I take h's. I take 4 h's. Good plan, because I want problems of size n over 4. Right? This has n over 4 leaves. This has n over 4 leaves. This is the root, by the way, in the middle. This has n over 4 leaves. This has n over 4 leaves. So I have 4 problems of size n over 4. Somehow I've got to get that down to 2. Thankfully, if I look at width or if I look at height, there's only 2 that matter. Right? And height, these 2 matter, and these 2 get along for free. They're going in parallel, just like we had with height over here. But I get that both in height and in width. If I measure, let's call this, well, now they're equal, so I'll just call them the length. We have L of n by L of n. And if I compute, well, what's L of n? I have here L of n over 4, because only a quarter of the leaves in this one or in that one. Then I have a constant, this is like theta 1, no big deal. And then I have L of n over 4 again. So I get the recurrence that I wanted. L of n is 2 times L of n over 4 plus order 1. And that has solution square root of n, as we claimed before. Again, we're in case 1 of the master method. Cool, huh? This is a much more compact layout. Charles, did you invent this layout? Or no, but I know it appears in your PhD thesis, and you extended it in various directions. So this is sort of a classic, cool layout of trees into grids, and another application of divide and conquer. I mean, this is not particularly useful for algorithms directly. It's useful for VLSI layout directly, but it gives you more flavor of how you should think about, if you know what running time you're aiming for. Like in problem sets and quizzes, often we say, here's the running time you've got to get. Think about the recurrence that will get you there, and that could inspire you. And that's it. Recitation Friday, for homework lab Sunday, no class Monday. See you Wednesday.